Welcome to section 4.1, composite functions. Objective 1, form a composite function. The definition of composite function states, given two functions f and g, the composite function denoted f composed with g is defined by f composed of g of x equals f of g of x. The domain of f composed with g is the set of all numbers x in the domain of g, such that g of x is in the domain of f. In other words, f composed with g is defined whenever both g of x and f of g of x are defined. Caution, f composed with g does not mean f multiplied by g. It means input the function g into the function f. F composed with g equals f of g of x. It does not equal f of x times g of x. So let's consider this figure below. Only those values of x in the domain of g for which g of x is in the domain of f can be in the domain of f composed with g. The reason is if g of x is not in the domain of f, then f of g of x is not defined. Because of this, the domain of f composed with g is a subset of the domain of g, and the range of f composed with g is a subset of the range of f. Okay? So only the values of x in the domain of g for which g of x is in the domain of f, okay, can be in the domain of f composed with g. Okay, so that's this intersection right here. All right. The reason is if g of x is not in the domain of f, so that would be this section over here, then it cannot be in the domain of f of g of x, which is what is right here on the side, sorry. If it's not inside this middle section, then it cannot be in the range of f of g of x. Okay. A second illustration is provided in this following diagram. All right. So here, x is the input for the function g, and this is yielding g of x as our y. Then g of x is in the input to the function of f, yielding f of g of x. Note that the inside function g in f of g of x is processed first. So you have an input x, you insert it into the function g, you then get your g of x, you then take g of x and you insert it into the function f, giving you the output f of g of x, which in other words is f composed with g. So now we're going to evaluate a composite function. So suppose f of x equals 3x squared minus 4 and g of x equals 5x. We are asked to find the following. Okay. So for a, we have f composed with g, and we're trying to evaluate it at the number 1. So just like in our definition, we are going to first start with g of x, take g of x, and then substitute it into f to find our expression. So we are first going to find g of 1. So we're going to substitute 1 into g of x. So that would be 5 times 1, and that would get us the value 5. Then we're going to find f of g of 1. So now we're going to take g of 1, which we know to be 5, and substitute it into the function f. So we'll get 3 times 5 squared minus 4. Okay? So that will equal 3 times 25 minus 4. When we evaluate that, we get 71. Okay? For b, we're taking g composed with f. Okay? So now we're evaluating g of f of x when x is 1. So we'll first take f of 1. So substituting 1 into f of x, we can evaluate. So that's 3 minus 4, which is negative 1. So now we'll take g of f of 1, which is g of negative 1, because f of 1 equals negative 1. So now we'll evaluate the function g of x when x is negative 1. So that'll be 5 times negative 1, which equals negative 5. Okay, so f composed by f of negative 2. So we'll first take f of negative 2. So we'll evaluate the function f of x at negative 2 and simplify. So we'll get 3 times 4 minus 4. So that's 12 minus 4, which is 8. Then we will take f of the value 8, of negative 2, which equals 8. Let's check that. Value at negative 2, okay, which is f of 8. So now we're substituting 8 into the function f of x. Okay, and so that's 3 times 64 minus 4. And that should get us 188. Okay. And then d, g composed by g of negative 2. So it's similar to c, except we're using the function g of x. So first evaluate g of x at negative 2. So that's 5 times negative 2, which gets me negative 10. Then g of negative 2, and that gets me g of negative 10. So 5 times negative 10 equals negative 50. Amazing. All right, so graphing utilities can be used to help us evaluate composite functions. We can use them to help us verify our results. So for our previous problems, we can use our calculators to solve those problems, and I'm going to show you how to do that for one of them. Okay, now other graphing utilities that you can use are GeoGebra and decimals. Very similar format as you see here presented in these images. But since we're using our TI calculators, I'll show you how to do that one. So let's go back to our problems. All right, and then let's pull up our calculator. All right, so let us do the first one, f composed with g of 1. Okay, so we're going to go to y equals, okay? Then in y equals, we're going to enter in both of our functions. So for the first one, f of 1, I'm going to place the f of x function. And for, not f of 1, y of 1. For y of 2, I'm going to enter in 5x, so the g of x function. So I have 3x squared minus 4, and I have 5x here. Okay, so now I have all of them entered in. Okay, so now I want to go back to the home screen. Okay, so now we want to enter in our two functions, y1 and y2. There's two different areas where you can locate this, so I'll show you both of them, and then we'll move forward. So the first way is to press alpha and then trace. This will pop up this bar on your screen where you are located in Y bars, where you see all of the different variations of Y. So we are going to be using Y1 and Y2 when entering in this composite function. The second way to find these variations of y is to, let me click out of this, to go to vars and then go over to y vars over 1 and then to functions. So that's number 1, or you can press enter. And now you have a list of all of your different y functions. So either way works. I will most likely be using the alpha trace feature, which is a shortcut to getting to y bars. All right, so we want to now evaluate f composed with g. F of x is my y1 and g of x is my y2. So first let's enter in y1. So alpha trace, and I'm going to select number 1. Then I will have a parentheses, and I'll go back alpha trace, and then y2. And I want to evaluate this at the number 1. Remember, f composed with g is equal to f of g of x. So in this case, y1 of y2, and I'm evaluating it at the number 1. So when I press enter, I should get the same value that I got algebraically when I did it by hand. And that value is 71. Note here that I also get 71. All right, so that's the way to utilize your calculator to find composite functions. All right. Objective 2, find the domain of a composite function. Okay, so recall that the domain of f composed with g is the set of all numbers x in the domain of g for which g of x is in the domain of f. Okay, so let's keep that in mind as we move into these examples. So suppose that f of x equals x squared plus 2x minus 5 and g of x equals 3x plus 1. We're asked to find f composed with g and g composed with f, and then find the domain of each composite function. Okay, so let's first find the domain of f. So the domain of f is going to be all the x values that exist within our function. Well, f of x is a quadratic function, so it's a parabola, and the standard for a parabola is all real numbers. So we'll write our all real numbers symbol, or you can write the set of all real numbers, either way. And the domain of g is a linear, well, g of x is a linear line, so the domain of g will also be all real numbers as well. Okay, so there's no restriction on the domain. So now let's find f composed with g of x, which we know is the same thing as f of g of x. So we're going to be taking the function g of x and substituting it into the function f. So g of x equals 3x plus 1. So I want to evaluate the function f when x equals 3x plus 1. Okay. So f of x is a quadratic. So wherever I see an x value, I'm going to enter in 3x plus 1. So I'll have 3x plus 1 squared plus 2 times 3x plus 1 minus 5. Okay. I can simplify this binomial that's being squared, and that will get me 9x squared plus 6x plus 1. I can then distribute the 2 to each term. So that's 6x plus 2, and then bring down the minus 5. Okay. I can combine like terms. So I have like terms here and like terms here. Okay. So I'll have 9x squared plus 12x and minus 2. Okay. So f of g of x is 9x squared plus 12x minus 2. So now I'm asked to find the domain of this composite function. So this composite function is also a quadratic. So its domain is going to be all real numbers. All right, now we're asked to find g composed by f of x. So we're now switching the two. Remember that the domain of f is all real numbers and the domain of g is also all real numbers. So I am trying to find g of f of x. Okay. So f of x here is equal to x squared plus 2x minus 5. All right, so I'm going to be entering in x squared plus 2x minus 5 in for all values of x in the g of x function. So that will get me 3 times x squared plus 2x minus 5 plus 1. So I'm going to distribute the 3. In other words, multiply it by every term within the parentheses. And I will have 3x squared plus 6x minus 15 plus 1. That equals 3x squared plus 6x minus 14. Similar to the last problem, this too is also a quadratic, and its domain is all real numbers. So g composed with f has a domain of all real numbers. So the previous example illustrates that in general, f composed with g does not equal g composed with f, though there are cases where the two compositions are equal. In determining the domain of the composite function, f composed by g of x equals f of g of x. Keep the following two thoughts in mind about the input of x. Any x not in the domain of g must be excluded. Okay. And any x for which g of x is not in the domain of f must be excluded. Okay, so if it's not in the domain of G, and if the domain of G of X is not in the domain of F, then it cannot be in the domain of F composed with G. Okay. All right. So let us do another example, keeping those two things in mind. So we're asked to find the domain of F composed with G if F of X equals 1 divided by X plus 4, and G of X equals 4 divided by X minus 3. Okay. So first, let's find the domain of G. So G of X has a denominator that cannot be 0. So X minus 3, if we set it equal to 0 to find the X value that makes the denominator 0, we would get the value 3. So the domain of G is going to be all X values except for when X is 3. Okay. Now for the domain of F, all right, we look at our function f of x. Similarly, we know the denominator cannot equal 0. So we'll set the denominator equal to 0 to find the x value that would make the denominator 0. In this case, it would be negative 4. So all x values except for when x equals negative 4. Okay. So for the domain of G, 3 is excluded from the domain of F composed by G. And then for the domain of F, G of X cannot equal negative 4. So we're going to have to solve for the equation G of X equals negative 4 to determine what additional values to exclude. Okay. So first, let's find the values that would get us negative 4 for G of X. Okay, so G of X equals 4 over X minus 3, and we want to set that equal to negative 4. So 4 equals negative 4 times X minus 3. We can distribute the negative 4. So 4 equals negative 4x plus 12. I'm going to add 4x to the right side and add 4x to the left side, subtract 4 to the right side. So that will give me 8. And so x gives me 2. Okay, so the domain of F composed with G is going to be all values of x except for when x equals 2 and when x equals 3. Okay, so just to review, we found the domain of G, okay, and we found the domain of F. So in the domain of G, which in this case is our x for our f of x, x does not equal 3. So we will never be inputting 3 into our function of G of x because it will be undefined. And then we can't take undefined and enter that into f of x. So 3 will not be in our domain. Now we found the domain of f. Okay, so the domain of f is the x, can be all x values except for when x is negative 4. So when f of x is equal to negative 4, when x is equal to negative 4, f of x does not exist. Okay, so we want to find an x value in G of x that could get us negative 4, because if we get negative 4 when we evaluate G of x at an x, and then we substitute in negative 4 into f of x, our value will be undefined as well. So once we find that x value in G of x, we won't input it into our composition because we would get undefined. So that is why we evaluated g of x at -4 in order to help us find the other x value that is not included in the domain. All right, let's do another one. So suppose f of x equals 1 divided by x plus 4, and g of x equals 4 divided by x minus 3. Okay, so this is similar to the one that we just did. We want to find f composed with g and f composed with f, and then find the domain of each composite function. Okay, so we know that the domain of f is going to be all x values except for when x equals -4, and the domain of g is all x values except for when x equals 3. So now let's find f of g of x. So f of g of x is equal to f of 4 divided by x minus 3. Okay? So I'm going to substitute in this ratio into f of x. So I'll get 1 divided by 4 divided by x minus 3 plus 4. Okay. I now want to, I can get common denominators in the denominator. So I will be multiplying the denominator, the value 4 by x minus 3. So I can get common denominators. So I have 4 plus 4 times x minus 3 all over x minus 3. So I have a complex fraction, and this can be rewritten as x minus 3 divided by 4 plus 4 times x minus 3. Okay. So I can simplify my denominator. So I have 4 plus 4x minus 12. So I can continue simplifying, because I can combine the 4 and the negative 12, and I'll get 4x minus 8, which in factor form will get us 4 times x minus 2. Okay. Now, f of g of x equals x minus 3 divided by 4 times x minus 2. That is the expression. But when we want to find the domain of f composed by g, or f of g of x, we want to also evaluate what x values will make the denominator 0, because it is a ratio. So we're going to set our denominator equal to 0 and determine those x values. So I'll divide both sides by 4. Then I'll add 2 to both sides, and I get x equals 2. So the domain of f composed by g is all x values except for when x equals 2 and x equals 3, because that is excluded from the domain of g of x. Okay, so that's the domain of our expression f composed with g. Awesome. All right, let's continue on to b. Okay, so we're asked to find f composed with f of x, remembering that the domain of f is all x values except for when x equals -4, and the domain of g is all x values except for when x equals 3. So f composed by f of x is going to be f of x. So we're substituting the function f into the function f. So f of 1 divided by x plus 4 Okay, so this would be 1 over x plus 4 plus 4. So similarly, I want to make common denominators. So 1 plus 4 times x plus 4, which will allow me to put everything over x plus 4. This is a complex fraction, which is equivalent to x plus 4 divided by 1 plus 4 times x plus 4. I can then distribute the 4 in the denominator. So 1 plus 4x plus 16. I can combine like terms in the denominator. So I have x plus 4 divided by 4x plus 17. So that is our expression for f of x. Similarly, I'm going to set my denominator to 0 like we did in the last problem, and I'm going to solve for x. So 4x equals negative 17, so x equals negative 17 over 4. So the domain is going to be all x values except for when x equals negative 4, because that's in the domain of f, and where x equals negative 17 over 4. Okay, because that would make our denominator 0. All right. So in this example, we're going to be showing two composite functions are equal. So if f of x equals 2x minus 5 and g of x equals x plus 5 divided by 2, we want to show that f composed by g of x equals g composed by f of x equals x for every x in the domain of f composed with g and g composed with f. So let's find f composed with g of x, and then we'll find g of x composed with f of x, and that will help us determine that both of these two functions are equal to x. So both of these two composite functions are equal to x. And then g of f of x. All right. So in the first one, g of x is our x, and we're going to substitute it into f. And then in the second one, it's the reverse. So we're going to take f of x as our x and substitute it into g of x. So we'll take f of 2x minus 5. Oh, no we won't. No we won't take that. That's not g of x. All right, let's take g of x, which is x plus 5, over 2. There we go. All right, and we're going to now substitute that into f. So that will be 2 times x plus 5 over 2 minus 5. Simplifying, the 2's cancel. So I have x plus 5 minus 5, and then I get the value of x. Then for g of f of x, I'm substituting in 2x minus 5 for x. So I will have 2x minus 5 plus 5 divided by 2. I can simplify the numerator, so that's 2x divided by 2, and that also equals x. So I've now shown that f composed with g of x and g composed by f of x equals x. So some techniques in calculus require the ability to determine the components of a composite function. So for example, consider the function h of x equals the square root of x plus 1. Letting f of x equal the square root of x and g of x equal x plus 1, we can write h as the composition of the functions f and g, because h of x equals f composed by g of x, which equals f of g of x, which equals f of x plus 1, which equals the square root of x plus 1. So we are asked to find functions f and g so that f composed with g equals h if h of x equals the quantity 3x squared minus 5 to the power 21. Since the function h raises the expression 3x squared minus 5 to the power 21, it makes sense to define f and g as f of x equals x to the power 21 and g of x equals 3x squared minus 5, where f of x is our outer function and g of x is our inner function. Then f composed with g of x will equal f of g of x equals f of 3x squared minus 5 equals 3x squared minus 5 at quantity raised to the power 21, which equals h of x. Okay. So can you think of another pair of functions whose composition would also equal h? Well, if we let f of x equal x to the 7th and g of x equal 3x squared minus 5 to the 3rd, then f composed by g of x will equal f of g of x, which equals f of 3x squared minus 5 to the 3rd, which equals 3x squared minus 5 to the 3rd raised to the 7th. 3 times 7 is 21, so that will get us 3x squared minus 5 to the power 21, which equals h of x. Okay, so there's different ways to express h in terms of one being an outer function and another being an inner function. All right, find functions f and g such that f composed with g equals h, where h of x equals 1 divided by x plus 3. So let's let f of x, since this is a ratio, equal 1 divided by x. Okay, and we'll let g of x equal x plus 3. So then f composed with g of x equals f of g of x, which equals f of x plus 3, which equals 1 divided by x plus 3, which equals h of x. Okay, all right. And that concludes section 4.1.